In this section, we discuss centripetal and tangential acceleration. First, let's look at the case of uniform circular motion, a situation where the angular velocity is constant. This means that there is no angular acceleration, and therefore no tangential acceleration, since the tangential acceleration is equal to the radius times the angular acceleration. A tension force from a guide wire provides the centripetal force that constrains a model airplane to a circular path. The centripetal acceleration that results from this force is directed radially inward and is given by AC equals Vt squared divided by r, where Vt is the tangential speed and r is the radius of the circular path. We know that the tangential speed is given by r times omega. Inserting this into the equation for centripetal acceleration, we have AC equals r omega squared divided by r, or AC equals r omega squared. Suppose now that the angular speed of the plane is changing. In this case, the motion can no longer be described as uniform circular motion, and there will be two contributions to the total acceleration: the centripetal component, directed radially inward, and the tangential component, directed along the tangent of the circular path. Note that the two acceleration components will always be orthogonal to one another. The total acceleration will be the vector sum of the tangential and centripetal components, and, since they are orthogonal to one another, the magnitude of the total acceleration will be given by the Pythagorean theorem as a equals the square root of ac squared plus at squared, where ac equals r omega squared and at equals r times alpha. Also, the angle between the total acceleration and the radially directed centripetal component is phi equals tangent inverse of at divided by ac. In summary, in terms of angular variables, the centripetal acceleration is given by ac equals r omega squared. In the case where there is also a tangential acceleration, the motion is considered as non-uniform circular motion, and the total acceleration is the vector sum of the centripetal and tangential acceleration vectors. Finally, since the tangential and centripetal components are orthogonal, the magnitude of the total acceleration is given by a equals the square root of ac squared plus at squared, and the angle between the resultant acceleration and the centripetal component is given by phi equals tangent inverse of at divided by ac.